Today we will work on something called binary search tree. Binary search tree is a specialized form of tree, which is a data structure, and binary search trees works as follows. There are nodes, and every node can have left and right childs. The trick is everything left of a node should be smaller than that, and everything right of a node should be greater than that. And today, given a node, we will check if it is a valid binary search tree or not. So let's see some examples of binary search trees. So let's say I have a root node, and let's say its value is 50. So according to definition, everything left of it should be smaller than it. So let's say I can write 11 here, and everything right of it should be greater than it. Let's say it's 19. So also 11's left and right childs should be lower and greater than 11 respectively. So let's say we have 7 here, and the right child of 11 should be greater than 11. But the important thing to note is it should also be smaller than 15, because everything left of 15 should be smaller than 15. So maybe it can be 30. And also here the left node of 19 should be smaller than 19, but it should be greater than 15 because it's at the right, it is gotten with the right child of 15. So maybe it can be 16, and maybe this can be 20. So in order to validate given a node, in order to validate a binary search tree, first of all we need a way to traverse it. And an easy way to traverse a binary search tree would be using a queue. So let's say that I have a queue, and first I get the 15, the root element, as element of my queue. After that, I would just remove it from my queue, and I would add 11 and 19, its left and right childs to my queue. So I check 15, then I am on 11, and I will remove it and add 7 and 13 to my queue. After that, I will remove 19 and add 16 and 20 to my queue. And after that, I will remove 7, 13, 16, and 20. And by this way, I actually traversed all of the nodes in my tree. So this is the way of traversing the tree, but we need to also check the greater and smaller comparisons while traversing the tree. So let me introduce a new way of thinking. Let's say we have a queue again, and let's say that we got 15 here. So the first node actually has no restrictions. It can be anything between minus infinity and plus infinity. So I will just write that to my queue. It can be anything between minus infinity and plus infinity. So I'll just remove it and add its left child. So while adding the left child, I will do something like that. The left child actually can be, the lower limit for a left child is actually minus infinity. But the maximum it can be is 15. So instead of plus infinity, I will add 15 here as an upper limit. Also, when adding 19, I will write 19. Here, we have no upper limit. It's actually infinity. But as a lower limit, I must write 15 because it should be greater than 50. So now this part is important because we will transfer the maximum and minimum information through here. So I'll just remove this from my queue, and I will add its left and right childs, which are 7 and 13. But while adding them, I need to look at these minimum and maximum and add their minimum and maximum accordingly. So my minimum was minus infinity when going to the left, so it's still minus infinity. But my maximum was 15, but now it is not 15, it should be 11 because this should be smaller than 11. And while going to the right, now my minimum is actually not minus infinity. My minimum is 11 now because I'm looking at the right child. Also, my maximum is not plus infinity, but 15 from here. Because in order to this to be a binary search tree, this node should also be smaller than this node, even it's at the right of the 11. So basically what I'm doing was I got my current value and my minimum and maximum value at some point, and while going to the left, I update my maximum value with my current value, and while going to the right, I update my minimum value by my current value, and this information actually goes to every child. So by that, this tree could be a more complicated tree and there could be many more nodes. But within transferring the information, I actually be sure that no child, left child of 15 can be greater than 15. So let's try to put this idea into code. So I'll just open Leet code here, and the function name is valid binary search tree. So what I want to do is I just have to define a queue. In Python, we can define a queue by using an array and pop with append and pop operations. So I'll just add the first element to my queue, which is my root element. And also I would like to have some max and min values. So let's say we have a max value and a min value. And actually their values are plus infinity and minus infinity. After that, I'll just, in a loop, I'll just iterate over this tree while the queue is not empty. So here, the thing we need to check is if my values are within maximum and minimum boundaries. So I'll just write if my, actually it's not the root value, but my current element would be the one I pop from my queue. So if my current element is value is smaller than equals to my min value, and my smaller than min value, and my current element's value is greater or equals to max value, then this means that this is not a valid binary search tree. So if this node is actually greater than its value is greater than min value and its value is smaller than max value, then I can go on traversing my tree. To do that, if my current node has a left node, then I'll just add to my queue. Also, I made a mistake here. In my queue, I will not just add my root node, but I would also add my current max and min values. And while popping from the queue, I would also get these max and min values, so I can update them every time I put them into a queue. So I will just append to my queue my left node. So at this point we are going to left, so that our actually maximum now should be my current node's value, and actually my minimum is what was my minimum before. I do not change my minimum. Also, if my node has a right child, I'll just append that right child. And since I'm going to the right, now my max value is my current max, but my min value is my current value. So this way, as I explained, I would add all of the nodes to my queue within their respective min and max boundaries, and I would check every one of them here. So if any one of them are out of these bounds, actually this is not a valid binary search tree. However, if this iteration is complete and it did not return false, then I would have to return true in order to complete the function, because it means that our tree is a valid binary search tree. When before submitting, let me just fix a small error here. This should actually be OR, because if any of these is wrong, we should return false. So let's just submit this. As you can see, we have a working solution here. What we did was basically, while iterating in a tree, we also added max and min values to our queue. So by that way, we didn't lose the information of higher parents of some node and also checked according to them.